Okay, welcome to the first introductory biochemistry video. Today I just want to discuss a pretty common topic that you'll probably encounter within the first few days of your introductory biochemistry course, and that is intermolecular forces. So I want to start out with just a little bit of background information, a refresher on intermolecular forces. So intermolecular forces are forces of attraction that exist between two molecules, and are much weaker compared to intramolecular forces. These forces exist when the molecules are in close proximity to each other. So just a basic definition of what an intermolecular force is. And the three most common types of intermolecular forces that you're likely to encounter in this class is hydrogen bonding, dipole-dipole interactions, and London dispersion forces. And to give you guys an idea of the difference in the energy required to break covalent bonds and disrupt intermolecular forces, I have this example. It says it requires 463 kilojoules per mole to break 1 mole of OH bonds in an H2O molecule, but only 44 kilojoules per mole are needed to separate 1 mole of water molecules in liquid water. So you can see right away that it requires a lot more energy to break a covalent bond than it does to disrupt these intermolecular forces. And we'll understand why that's important once we get to the questions I prepared. So the first question I have here says, what are the requirements for molecules to form hydrogen bonds? So for a bond to be called a hydrogen bond, it must have a weakly acidic NH-OH or FH, which then forms a hydrogen bond with a weakly basic ON or F. So basic understanding of hydrogen bonding, nothing spectacular. I'm sure most people have encountered this in introductory chemistry classes. The second question says, define the hydrophobic effect in your own words. So the hydrophobic effect refers to water's tendency to minimize its interactions with nonpolar or hydrophobic molecules. Thus, these molecules are excluded from aqueous solutions. So the hydrophobic effect will become more important as we start looking at protein structure and understanding the three-dimensional structure and how proteins fold. So it's a good idea to get accustomed to it and understand what it is early on. The third question says many properties of acetic acid can be rationalized in terms of a hydrogen-bonded dimer. Propose a structure for such a dimer. So the first question you might have is, what is a dimer? It's a chemical structure formed from two subunits, in this case two acetic acid molecules. So the first thing I would do with a problem like this is I would draw acetic acid. And since we're forming a dimer and we know it involves two subunits, we're going to draw two acetic acid molecules. And I'm going to draw them in a specific way. Might look kind of strange right now, just because, but it will make sense in a minute. So the thing to realize about this is that we have the conditions to form hydrogen bonds. And basically, to form the dimer, all we have to do is show that hydrogen bonds are forming between the carbonyl group of one acetic acid molecule and the hydroxyl group of the other acetic acid molecule, and vice versa. So I'll do that by showing a dotted line connecting the hydrogen from one hydroxyl group to the oxygen of the carbonyl group. And that's basically it. That's a cyclic dimer. So the final question I have says, why does the central role of weak forces, hydrogen bonds, London dispersion forces, etc., in biomolecular interactions restrict living systems to a narrow range of environmental conditions? So my response to that is, biomolecules can only function under a very narrow range of environmental conditions. Factors affecting the environmental conditions include temperature, ionic strength, and relative acidity. Any extremes in these conditions can disrupt the weak interactions, maintaining the structure of these molecules. The loss of structure results in a loss of function. So the key thing here is that the loss of structure results in the loss of function. That's a big picture concept for the entire course, and it will become, again, important when we start discussing protein structure. So that's all I want to talk about for this video, and we'll be coming back with acid-base chemistry and some other concepts that are usually covered within the first couple of days of an introductory biochemistry course. So thanks.